Unit 4, exponentials and logarithms. 4.1 is exponential functions. We start with a pretty basic problem. It says for f of x equals 4 to the x. So we're looking at this exponential. Part A says find f of negative 2. So really all we're doing is plugging in a number. We want to do 4 to the negative second power. Now you can use a calculator for this, but I'd rather you learn what a negative exponent does. A negative exponent is just a reciprocal. So what I can do here is take the reciprocal of 4 and square it, okay? So reciprocal and square it. That's going to be 1 over 16. Problem with using a calculator on that is it's going to give you a decimal number. This is probably more, I don't know, in line with what they want. 1 over 16. F of 5 just means we want to take 4 to the 5th power. Now an exponential, an exponent is repeated multiplication. So that's 4 times 4. We don't need to write this down, but that's 4 times 4 times 4 times 4 times 4. That's what an exponent does, right, is repeat multiplication. I don't want to do that in my head. I'd rather just use a calculator. So 4 caret 5, I'm using a calculator all day long on that, is 1024. Exponents. The next one's, I don't know, quite a bit harder, I guess. You're plugging in 2/3, and so we're looking at 4 to the 2/3 power, and we've got a fractional exponent, and a fractional exponent does a couple of things. You can look at it as 4 squared, and then take the third root of that if you want to look at it that way. Or you can look at it as the third root of 4 and then square it. You can look at it either way. I think the easiest way, though, in this case is probably just to type it in, all right? So what I would do here is say 4 to the, but then if you want to enter a fractional exponent on your calculator, you're going to want parentheses. You don't want to just do 2/3. You want to do parentheses 2/3, like that. And it gives me a crazy looking decimal, and I don't know, in this, sometimes you can simplify it and make a nice number, but in this case it doesn't look like you can. So I'm going to be satisfied with this decimal number. Let's round off to 4 decimals, 2.5198. So let's put approximately 2.5198. Next one's more obviously a calculator problem. We're going to do 4 to the 2.15. Only thing you're going to do is calculator. 4 to the 2.15. Kind of weird to think about repeated multiplication here. That's what an exponent is. We're multiplying 4 times itself 2.15 times. I don't even know how to imagine that. But we get what, 19.6983. And let's put a little approximately here so that we understand that that's not exact. Sometimes Math Excel is going to make you say, write the exact answer. That's not going to work. We'd have to do something else. Next, we're going to graph functions and give domain and range. And so when we graph exponentials, you should recall that you're going to have like growth or decay. Exponential growth or exponential decay. I didn't spell that right. And you should know that a growth is going to look like this, and a decay is going to look like this. That's kind of what it looks like. Let's make that flatter. And you're going to have something called an asymptote, which is like a boundary line. And that thing is going to stay above that boundary line, that asymptote. And that's kind of what a graph looks like. So you want to, I guess, identify if it's a growth or decay. That might be your first step. And a decay problem is going to have a base number that's in between 0 and 1. Now, if you have a negative, it'll be between -1 and 1, I suppose. But most people remember it as a fraction. So it's not technically true. You wouldn't necessarily have a fraction as long as it's a number between 0 and 1. So if I have like 2/3 to the x, or in this case 1/2 to the x, either way, that's going to be decay. So why that's important is because I already know what the graph looks like. Yes, you could type this in on Desmos, but we're gonna figure out how to graph this by hand first, and then we can use Desmos anytime we want. So basically, we're gonna go way back to the first way we ever learned how to graph was plugging stuff in. All right. So let's make an XY table, and let's just plug stuff in. Okay. You can plug in anything you like, but a lot of the time 0 is a good number to plug in because we know something to the 0 power equals 1. So I've got 0, comma 1 is a point right there, 0, 1. And a lot of the times people like plugging in 1 because it's easy. 1/2 to the first power is just 1/2. Okay, so we've got 1, comma 1/2. Now keep in mind, remember what the decay graph looks like. We already know what this looks like. We're just trying to find enough points to where this fits. So then people are going to plug in 2, and they get 1/2 to the second power, and that's 1/4. And now it's getting kind of hard to graph. 2, comma 1/4. You just kind of have to eyeball it. Yeah, that looks like 1/4. It's actually maybe easier in this case to use negative numbers. If I plug in -1, I do 1/2 to the negative first. Remember what that negative exponent does is a reciprocal, okay? If you flip it, if you take a reciprocal, you're actually going to have 2 to the first power. So that's 2. -1, comma 2 is right there. And let's do one more. Let's do -2. If we have 1/2 to the negative second power, that negative exponent is a reciprocal. So flip it. Flip it. We're going to flip it and square it. 2 squared. That's 4. So -2, comma 4. I would say that's plenty enough to draw this graph. I know pretty much what this looks like right now. I already knew what a decay was, but now I'm even better. So what you might consider doing, draw that asymptote in there. That's just kind of a boundary. You've got this asymptote at y equals 0, and that's a boundary line. Make sure we don't cross that boundary line. We're going to have a curve that looks something like this and curves down here and gets kind of flat to that asymptote. There's your exponential decay function. Now, we also have to give the domain and the range. The domain and the range, remember how we kind of think about this is if you like squashed it, if you squashed it onto the x-axis, only look at the x numbers, that's the domain. And so in this case, since this thing is going to the left, to the left, to the left, it's going to end up covering the entire axis. It's kind of hard to tell. It's kind of hard to tell, I think. This is going to be all real numbers for the domain. I think it's probably better if you learn the actual definition of a domain. The actual definition of domain is, what am I allowed to plug in for x? What could the x numbers possibly be? And it's like, are there any problems? Am I allowed to, am I going to have a 0 on the bottom of a fraction? Nope. Am I going to have a square root of a negative number? Nope. I'm not going to have any issues. I'm allowed to plug in whatever I want. That's domain. That's why it's all real numbers. Now we look at range. I think it's a little bit easier to think about when we squash onto the y. If you take this graph and you squash it onto the y, it's only going to cover from 0 and up. From 0 and up. And so that is your range, is from 0 to infinity. Not all real numbers. All right, so once you've seen one, they start going quicker, I think. You look at the next one. And the next one, since this one is a number 3, I know this is a growth problem. This is growth. But that negative just tells me that it's going to be a flip. It's a growth problem, but it's going to be flipped. So instead of looking like this, it's going to be flipped and look like this. It's a growth with a flip. So I already pretty much know what it looks like. Let's just plug some numbers in so we can make sure. So again, 0 is almost always going to be a good number to plug in. -3 to the 0 power. All right, you got to be careful though. The negative is not a part of my exponential. Really, you should think of it as -1 times 3 to the x, I suppose. The base is 3. We're taking that 3 to the exponent 0, and so this is going to end up being -1, not +1. That's -1. I've got 0, comma, -1 right there. And if you do 1, you got -3 to the first. That's -3. So 1, comma, -3. And you can already tell this is going to look like what I thought it was going to look like. That red little sketch that I drew before. This is what it looks like. If you want to do 2, you're going to have -3 squared. That's -9. Notice we're not squaring the negative. It's not -3 times -3. It's the opposite of 3 squared. That's really how it is. It gets confusing because people don't understand the difference between a negative and an opposite. This says the opposite of 3 squared. That's -9. So 2, comma, -9 is down here. Let's try a negative number. Let's try like -1. You got the opposite of 3 to the negative first. Negative exponent flips it, so that's -1/3. You got -1, -1/3. And you can do another one if you want. -2, that's the opposite of 3 to the negative second. That's the opposite of 1/9. You flip it and square it. You flip it and square it. That's what you do. So -2, comma, -1/9. That's really hard to draw, but that's about right there. Okay, we have this horizontal asymptote right here, again, at y equals 0. And our graph is going to flatten to that. Now that never gets vertical. So that thing that I drew at the right side of my graph is not vertical. It's still got some slope to it. That's how I know that the domain is going to end up covering everything. -infinity to +infinity. That's all real numbers. And the range this time, we don't start at 0 here. We start at the smallest number. The smallest y number would be -infinity. It's going from all the way down at the bottom, -infinity, up until 0. And it's a parenthesis because it will never equal 0. All right. Number 3, you've got a little bit of transformation. You should remember from algebra class that this is a transformation. And it's saying we can shift the whole graph to the right by 2. What I see is 3 to the x shifted right 2. Or I see a growth problem that's going to be shifted right 2. So if your normal growth looks like this, we're just going to take that whole graph and shift it to the right by 2. That's what it's going to look like. So you can almost draw your asymptote before we even start, because it's still going to have an asymptote at y equals 0. But now we need to come up with some points. And so I don't know how many points you need. I've been doing like 3 or 4 or 5. It's just as many as you need to be able to draw a good graph. So this time, if you pick 0, that may not be the best number to pick, because it's not 3 to the 0, it's 3 to the 0 minus 2. That's 3 to the -2nd power, and that's fine. We should be able to deal with that. 3 to the -2nd. Flip it and square it. Flip it and square it. It's going to be a fraction 1/9. So I've got the point 0, comma 1/9. Do your best. I know it's kind of hard to graph that. The graph's not big enough to do, but just do your best. In this case, I actually think 2 would be the best number to pick, because when we do 3 to the 2 minus 2, that's going to end up being 3 to the 0, which is 1. So 2 comma 1. And so then let's do, like, I don't know, 4. Let's say we do 4. 3 to the 4 minus 2. That's 3 squared, which is 9. Okay, 4 comma 9 is up here. I feel like that's probably good enough. I know what this thing looks like already. It's going to be flat to the asymptote, and then it's going to curve up and hit these dots. Something like this. Domain, Everything. Range, look at your y values. Y values go from 0 up. So 0 to infinity. Next one. Last graph. Graphing's not my favorite, but anyway, here we go. Last one of the graphs. You should see that this transformation says we're going to go left 2, but this transformation says we're going to go down 2. We've done transformations before. You've done them before in multiple different classes. I can still see that this is a growth problem. It's a growth problem, so I know it's going to look like this. I just know that it's also shifted left 2 and down 2. So if it's shifted down 2, that does something special. It does something weird to my asymptote. Instead of an asymptote at 0, like all of the others, everything is getting shifted down 2. So your asymptote gets shifted down 2 as well. And so now, instead of having an asymptote at 0, like all the others, we'll have an asymptote at y equals -2. That's the base. That's the baseline of our graph. Other than that, we're treating them all pretty much the same. Plug in enough numbers to where you can get a good feel for the graph. I actually think -2 is a pretty good number to pick. Think about why. If I go 3 to the -2 plus 2 minus 2. -2 plus 2 is 0, so I've got 3 to the 0. -2, that's 1 minus 2 is -1. -2, comma -1 right there. Is that enough to draw a good graph? Probably not. Let's try 0. You can do some of this in your head and not write it down if you want. 3 to the 0 plus 2 minus 2. That's going to be 3 squared minus 2. That's going to be 9 minus 2. That's 7. 0, comma 7 is right there. Is that enough to draw a good curve? I already pretty much know what it looks like. So, yes. I don't know. I know what it looks like. It's going to be flat. It's going to curve up and look like that. All right. So are 2 points going to be enough? Sometimes. 5 points enough? Usually. It just kind of depends. If you know what you're doing, 2 points might be enough. All right. But there you go. Oh, domain and range. Is this domain going to be all real numbers again? Yep. What about the range? -2 to infinity. Very good. This one doesn't start at 0. This one starts at -2. -2 to infinity. Very good. All right. I like these questions a little bit better. It's more interesting. We're solving. A lot of algebra class is about solving. Maybe we're going to solve something that you didn't know how to solve before. So the key in these problems, I think, is to get the bases to match. So 5 to the x, there are other ways to solve this, but today we're gonna do it this way. Maybe next time we'll do something different. I know 125 is 5 to the third. And it's kind of nice to have a base 5 on both sides because you can compare them. All right. But the problem here is that 5 to the third is on the bottom. All right. Really, we can look at this if we want as 1/5 to the third power. So I've got 5 to the x equals 1/5 to the third power. What I would really like to do is change this 1/5 into a base 5. I know 1/5 is 5 to the -1st. And so you can look at 1/5 to the third power as 5 to the -1st to the third power. Well, we know about exponent properties. That's going to just multiply those two exponents. That's 5 to the -3rd. So bringing this down, 5 to the x equals 5 to the -3rd. At this point, it should be obvious what's going to happen. You just look at your exponents. This exponent has to equal this exponent. That's your answer. X equals -3. Now, you can do this problem faster if you understand the idea of a negative exponent flips it and, in this case, cubes it. So you might be able to jump from here all the way to here if you really know what a negative exponent does. 1 over 125 is 5 to the negative third. Yes? Where did I get 5 to the negative 1? Because, okay, I know that 1/2 equals 2 to the negative first power. That's what a negative exponent does, is it flips it. I know that 4/3 to the negative first is the same thing as 3/4, because a negative exponent just flips it. So when I have that fraction like 1/5, it's useful to me to call that 5 to the negative first, because I'm trying to get a common, I was trying to make it match with this 5. If I can make those two bases match, that's what I'm trying to do. Now, I know that's confusing. I think the next example is even though it looks more complicated, I think it's easier to understand. When you look at number 5, you see that 3 and that 9. We want those two to match. So what I want to do here really is take that 9, and really I want to think of it as a 3 squared, because I want those two things to match. If I can make them both 3s, then I can compare them. So the left side of my equation says 3 to the x plus 1. I don't really need to do anything with that. But the right side, I've got this 9 right here, right? 3 squared is 9 to the x minus 3. If you can get a matching base, then you've really done everything that you need to do, all right? Because at this point, when these 3's match, you really just need to compare the exponents. I don't like that line there. X plus 1 is going to equal whatever 2 times x minus 3 is. The whole key was getting those things to match, okay? So simple solve here, we're going to distribute. That says x plus 1 equals 2x minus 6. Do what we've done a million times before. Subtract the x over, add the 6 over, 7. X equals 7. Now, if you don't understand that, let's do another example real quick, okay? If I said 5 to the x equals 25, okay? 5 to the x equals 25. One way to do this problem is to say, well, I know I can change 5 into or 25 into a power of 5. What is 25 written as a power of 5? 5 squared, right? 5 squared. So that means x must equal 2. That's the answer to this, right? X must equal 2 in order to make that 25. That's all I'm trying to do. Now, both of these examples were more complicated versions of that, but that's all I'm trying to do. So if I said 2 to the 2x equals 16, can you make 16 into a power of 2? Like 2 to the 4th power? 2 to the 4th power is 16. If you can make those 2's match, then all you have to do is compare the exponents. 2x equals 4, so that means x must equal 2. That's all I'm trying to do. I know these two problems have been more complicated versions of that, but that's all I'm trying to do. All right, so let's move on. Number 6 is a little bit different because the variable's not in the exponent. So this looks more like something you've probably solved before, even though it's a fraction. I'm going to rewrite x to the 2/3 like this equals 25. It's not the same problem. You can't make a 25 match with an x. You can't do it that way. But what we can do is kind of like make the exponent go away. What you can do is, let's take both sides to the 3rd power. Because the properties of exponents say we multiply 2/3 times 3, and those 3's are going to cancel out. If I take both sides to the 3rd power, that's going to cancel out that denominator 3. I'm left with x squared equals whatever 25 to the 3rd power is. Well, let's call 25, let's just call that 5 squared. That's going to make this easier. So instead of 25, I say 5 squared. You don't have to do it this way. I think it'll be easier for me to do this without a calculator, though. All right. So I've got 5 to the second to the third power. Well, again, your properties of exponents would have you multiply those. X squared equals 5 to the sixth power. And then if I want to ISO the variable, I would just take the square root, right? Square root. Actually, it's plus or minus square root. Anytime you square root both sides, you got to do the plus or minus, because there's going to be two solutions. X is going to equal plus or minus whatever the square root of 5/6 is. But you may remember some properties of exponents like this. Square root, you're going to take this and you're going to, anybody remember? Divided by 2. Square root of 5 to the 6th is 5 to the 3rd. So that's going to be plus or minus 125. Tough stuff. Now we're going to get into something completely different. And what's good about it is it's just a formula you're going to plug and chug. What's bad about it is you have to know which formula to use. All right. So I've got 2 different formulas that I can use, and it depends on how many times the interest compounds per year. We're talking about compound interest. And it's either going to compound some number of times or continuously. So first formula looks like this. A equals P times 1 plus R over N to the N T. That's an exponent. N times T is an exponent. For continuously, it's going to look similar but different. A equals P times E to the RT. That's actually easier to type in, but you have to understand that E is a number. You've got the E button on your calculator. E is a number. Kind of reminds me of pi almost. We all know pi is about 3.14. Well, E is a number that's about 2.7 or so. All right, E to the first power is that. That's a number. It's Euler's number. It has a lot of different applications in math and science. That's not important right now, but that is a number. E is a number, not a variable. All right. So what do the variables stand for? A is the final amount. P is the starting amount. R is the interest rate. N is the number of compounds. It's going to tell you it compounds twice a year, 4 times a year, 6 times a year, whatever that number is, however many times they calculate the interest. That's what N is. And T is time in years. These problems are going to look challenging, but it doesn't have to be difficult if you pay attention and plug stuff in where it needs to go. Number 7, $2,500 is deposited in an account. Okay, time out. Is that what we started with or what we ended with? 2,500. That's what we started with, so that's P. Okay, in an account paying 3% per year. Well, that's your interest rate, right? So R equals 0.03. 3%. You should know this, but maybe you don't. Percent means divide by 100. That's why we have to move the decimal, because it says 3 divided by 100. That's literally what it says. 3 divided by 100 is 0.03. Compounded semi-annually, you're going to get a word like this. That's the number of compounds. That's telling you how many times they calculate the interest. N equals 2. Find the amount in the account after 10 years. So that's time, T equals 10, with no withdrawals. All right. Find the amount. Find the amount in the account after 10 years. They're asking me to find the final amount, right? You have to be able to translate. And when you read that, you have to be able to say, well, they're giving me this, 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 and this, and I'm trying to find this. Otherwise, it's just a plug and chug. We've got this formula. How do I know it's this formula? Because they give me the n number. The other formula is going to be continuous. It's not going to be twice a year, 6 times a year, 4 times a year. It's just continuously. I'm going to use the other one. But in this case, they're telling me twice a year. I know what n is. I use this formula. Plug and chug. 2,500 is the P. The rate was 0.03. N was 2. N was 2. T was 10. Get you a calculator with parentheses on it. If your calculator does not have parentheses, I would not use it. So I just type it in right there, 2,500 parentheses. 1 plus 0.03 divided by 2. Close them. Exponent. And the only thing weird I would do here is I'd just say 2 times 10 in my head is 20, just to save myself some calculator errors. I know that's an exponent 20, so just, there we go. Okay. You should get $3,367.14. 3367.14. That's the final amount. Part B, how much interest is earned? You should already know this, but the interest is just whatever you ended up with minus whatever you started with. It's how much you gained, right? All right, so it's just the final amount minus the starting amount. You can box that in if you want. That's a formula, but I think you should just know that because you know what interest is. A minus P, that's going to be 3367.14 minus, what do we start with, 2,500? 867.14. That's the interest, or how much we gained by doing this investment. Number 8, Brendan must pay a lump sum of $15,000 in 8 years. What amount deposited today at 2.4% compounded annually will give $15,000 in 8 years? First thing I would do is just kind of go through and see what they give me and what they're asking. All right, what amount deposited today? When they say what amount deposited today, which letter is that? Are they asking me for the final amount or the starting amount? Starting amount. Okay. They're telling me in this problem that we're ending up having to pay $15,000 in 8 years. So we're going to end up with 15,000 or at 15,000. We started at I don't know what. That's what we're trying to figure out. Obviously, this is the rate. Move the decimal 2 times, divide by 100, however you want to think about that. And what do we have? 15,000 is the A. Okay. What about N? Compounded annually. How many times a year are they compounding this? Just once, 1 time a year. That's what that says. And that's kind of hidden in the problem. But when they say this, they're saying we're only going to compound it 1 time. So we need that number. I know it's this equation, A equals P times 1 plus R over N to the NT. You don't have to have that memorized, but I've seen it enough where I have it memorized. But I know it's that one, not the other one. Be careful. You got to put the numbers in the right place. This time they're giving me the A number. They're giving me the final amount, and they're asking for the starting amount. Got 1 plus 0.024 over 1 to the 1 times 8 years. So you can clean that up if you want to. 15,000 equals P times, that's just going to be 1.024 to the 8th power. To me, I think the easiest thing to do is not do 1.024 to the 8th power yet. to me, I think the easiest thing is just fall back on my algebra skills. If I want to know what this p is, I'm going to end up having to divide by whatever that is, right? And you can calculate it before, or you can calculate it later, but I think it's easier to just wait until later here. I know that p is going to equal whatever 15,000 divided by 1.024 to the 8th power is. And so I'd rather just type it all in my calculator at once. You don't have to do it that way, but that's what I would do. 15,000 divided by 1.024 to the 8th power, 12,407 and 71 cents. 12,407 and 71 cents. Last thing I would do on any of these problems is just make sure your answer makes sense. Does it make sense to have started with that amount, invested it, and ended at 15,000? Yeah, I'd say so. I mean, I can't do the problem in my head. I can't do the math in my head, but I could say that makes sense. Starting at 12,000, ending at 15,000. Okay, yeah, sure. Part B. If only 12,025 is available to deposit now, what annual interest rate is necessary for the money to increase to 15,000 in 8 years? Okay, so this one's a little bit harder. Write small. I might not have enough room here. But they're telling me the p-value. If only 12,025 is available to deposit now, what annual interest rate? So they're asking me for R to increase to 15,000 in 8 years. All right, so I know the final amount and I know the time, and we're still talking about annual, so n is still 1. It's still going to be the same equation, but this time I want R. So the formula says, oops, final amount equals starting amount. I'm trying to write small here, sorry. Times 1 plus, I don't know the rate, so I'm going to leave that variable in there, R, over 1 to the 1 times 8. Still, I'm just doing them all the same. I fill in what I know. Hopefully there's only one variable. I can find that variable. So cleaning up a bit, that's going to say 15,000 equals 12,025 times 1 plus R to the 8th power. 15,000 equals 12,025 times 1 plus R to the 8th power. Essentially, I'm just trying to solve. I'm trying to ISO the variable here. There's only one variable, so I should be able to ISO. I'm going to divide. Let's divide both sides. And I'm going to use my calculator here. 15,000 divided by 12,025. And so I get that. I'm going to leave that in my calculator, but I'm only going to write down like some of it. 1.2474. 1.2474 is approximately now 1 plus R to the 8th power. Trying to isolate the variable. If I'm going to isolate the variable, eventually I'm going to have to subtract 1, but first I need to get rid of that exponent, 8, okay? I'm going to get rid of that exponent in this way. I'm going to take both sides to the 1/8 power. If I take both sides to the 1/8 power, that's going to cancel out my exponent 8 because the properties say you multiply those, and that's going to just be 1. So I'm going to take both sides to the 1/8 power, which means we're going to need to take that number that's in my calculator to the 1/8 power. So I'm going to hit this caret button. So my answer to the, and anytime you do a fractional exponent, you'll want parentheses. So parentheses 1/8. That's taking that number to the 1/8 power. 1.028018. 1.028018. is approximately 1 plus r. I'm just trying to isolate the variable, so I'm going to subtract 1 to isolate that variable. Subtract 1, subtract 1. R is going to be approximately 0.028. Well, there's my rate right there, right? This is about 2.8%. Number 9, suppose 8,000 is deposited in an account paying 5% interest compounded continuously for 6 years. Find the total amount on deposit at the end of 6 years. The key here is continuous. As soon as I see that word continuous, I know I'm using the PERT equation. So let's just figure out what they're talking about here, what each number is. 8,000 is deposited in an account, so that's got to be P. And paying 5%, that means R is 0.05. And 6 years, so that's time. And it says find the total amount. That means we're finding this A value. All right, so let's just plug that in on a calculator here. Remember, E is just a number. Find that E button on your calculator, 8,000 E to the, I might put this in parentheses, 0.05 times 6. 10,798.87. Next, if current trends of burning fossil fuels and deforestation continue, then future amounts of atmospheric carbon dioxide in parts per million will increase as shown in the table. The data can be modeled by this function. What will be the atmospheric carbon dioxide level in 2015? So in this question, all we're doing is taking this number and plugging it in for x. So we want this. Where we plug in 2015. And we get 414.6, or about 415 parts per million. Part B says use a graph to estimate when the carbon dioxide will be twice what it was in 2000. Twice what it was in 2000. So if you look at 2000, we can see that it's 375. So take that times 2, 375 times 2. We want to know when it reaches 750. And so 750, can kind of think about where it's at 750. Okay. So let's look at a graph. I'm going to go to Desmos. And let's type in that equation. Okay. Notice we had to zoom. Like I've already got mine zoomed, but yours is probably here. So you zoom way out until you can see what it looks like. But right here, what I want to know is where does it equal 750? And so y equals 750 is right about here. And so it looks like I'm in the year 2112. All right, 2112 is where it's going to get to 750, 2112. So this exponential growth should be flatter right there. So we're looking right about here. We don't have to be super accurate, but we're looking, where does it equal 750? Looks like it's in the year 2112. And if we go back and look, 750 should fit, in here somewhere. So 2112, yeah, that seems about right.